Hey everyone, welcome to our AI and ML podcast. I'm Michael.
And I'm Emma. Today we're diving into some fascinating stuff in the world of machine learning.
Absolutely. We're going to explore the Jacobian and Hessian analysis. It might sound a bit intimidating, but I promise it's really cool once you get into it.
Right, so let's start by breaking down what the Jacobian and Hessian actually are. In simple terms, the Jacobian is a matrix of all first-order partial derivatives of a vector-valued function.
Exactly. And the Hessian comes into play when we talk about second-order partial derivatives. It gives us a way to understand the curvature of our loss function's landscape.
That's a great point, Michael. So when we're optimizing our models, these tools can help us analyze how steep or flat the loss surface is at any given point, right?
Yes, precisely. This is crucial because it impacts how our learning algorithm adjusts the parameters during training. A steep region might mean large updates, while a flat region suggests smaller adjustments.
And that definitely ties into concepts like gradient descent, which many listeners might be familiar with. If we're not careful, we could overshoot the minimum if we don't consider the landscape effectively.
Totally. And speaking of practical applications, these derivatives help in model tuning, especially in optimization problems like training neural networks.
Exactly. They can also be applied in techniques like Newton's method for optimization, which uses both first and second derivatives to converge to the optimum more efficiently than gradient descent alone.
Nice, let's not forget that these concepts are not just limited to neural networks. They're also widely used in fields like robotics and control systems. For instance, understanding movement dynamics and optimizing motion paths.
Right. And in computer vision, they can assist in feature extraction, where understanding how features interact helps improve model accuracy.
You've made some solid points, Emma. It's fascinating to see how deep this topic goes and how it's intertwined with various other fields. From optimization techniques to robotic controls, it's everywhere.
Exactly. And I love how mathematical theory gets translated into practical tools that enhance machine learning models. It makes the blend of math and AI so exciting.
For sure. So, as we wrap up, do you have any final thoughts on why understanding these concepts is pivotal for budding ML enthusiasts?
Absolutely. Grasping Jacobians and Hessians not only adds depth to your mathematical toolkit, but also equips you with the ability to fine-tune models more effectively and understand their behavior.
Well said. Thanks for tuning in, everyone. We hope this discussion gives you some insight into the beauty of machine learning theory.
Yes, stay curious and keep experimenting with what you've learned today. See you next time.